We're just gonna go for it. We got good to go. Okay. So all right, welcome to the video. We are going to extend our interpreter runtime a little bit here in our language. So let me open up the compiler itself here real quick, and then let me also open up in a different window the file we're going to be working on. The first thing I'll do, I'll actually build the LSP just in case that's going to work for us. And we will run into test source / suite 1 main. So what I've been doing is implementing this language feature. Well, let me go to static runs to be more interesting. Compile time compilation. Compile time execution. You can run pretty much the entire language at compile time. It doesn't, it runs it in a stack-based VM down to the bits. So you can work with pointers, call malloc, the whole thing. Which means you can call pretty much any code at compile time, which is really neat. And there's a lot of plans I have for metaprogramming specifically with this. I think Zig and even Rust and C++ to some extent with their const_expr and const have proven this is just a great idea. There's also Jai, which is unreleased, but also kind of started this craze. But anyway, what I have here is a showcase of I just sort of build up, okay, well, let's just statically do an int literal. Okay, I actually already had that because you have constants and it's pretty obvious that, okay, I don't need to execute this thing. And then it's like, well, what if I did 2 + 2? Okay, you do binary ops, right? It's like, well, what if it references another global? Well, it should probably be able to do that. Okay, we got to run the other global, right? And then what about function calls? Okay, so we got to do function calls. Okay, what about blocks, right? What if the function doesn't just return 2? What if the function has a few statements? All right, now we need to execute statements. Now we have variables. Now we need a stack. Well, we can just fake a stack. We'll just do a hash map, right, of the variable ID to the value. And that works for a little while until someone wants a reference to a thing on the stack, and the function they're calling wants a pointer, right? And so slowly what I've done is gone from a very fake, naive version of executing this language to a much closer to the metal VM. In fact, first I called it interpreter. I wanted to call it VM. I was like, this really isn't. This is just kind of, pretending. And then as I've added, more of these low-level concepts in and moved it to be stack-based, things like that, more memory-based, I did rename it back to VM. So, and what's next? So this program, let's just go through. So this comes later because it's a very advanced use case. But we have a function called getPoint, which returns a struct with a layout that definitely has padding. That's relevant. For static, hello static, the string literal actually makes a struct. So, in K1 string, here in the built-in string is a buffer of characters, and buffer is our contiguous allocation type. It needs to be renamed. Buffer worked better when data was an opaque pointer, but this really is kind of going to be our slice. Although I don't like slice because it implies that the thing is not whole. But I'd be swimming upstream on that one to not call it slice. Anyway, so we have our buffer, and string is just a length and a data pointer. And, so running this, what it means though is when this static code finishes running, we get back a value, right? And then what what does the type checker, what does the compiler do with that value? Because that value is, at this point, it's actually a pointer to a string that's on a temporary stack of a VM that we're about to destroy. So what we do is we read the VM value out into a limited sort of value language, value representation of the language that we call static values. So this static value, this does not represent everything the VM can do. The VM does the entire language, but these are the things that if the VM outputs them, we are able to serialize them effectively. So, or reify them is a way I like to think of it. Another way to say it is if I get one of these values, I can actually embed it in the LLVM-IR. I could embed it in the binary, like as data. So one thing we don't allow is pointers. Like you can't just say, here's a pointer, because it's not going to point to anything useful at runtime. We do allow the null pointer because that's a very useful static value to think about. A lot of globals are initialized to the null pointer. But if you want to talk about a value, then you actually need you need to return either one of our scalars or a struct or an enum. And then we support buffer. So if the struct is a buffer, we actually load all of the values from memory, from the VM's memory, and instantiate static values for each of those and then turn them into the pool. So if we were to return, like this example is doing, the buffer 1, 2, 3, 4, 5, that actually becomes just a Rust vec of value IDs where each of these values has been interned. And obviously that's going to get a little bit slow, but we're going to be putting, kilobytes or megabytes of data, I would think, in here. And these static values, not gigabytes. And honestly, even if it were gigs, it's probably not going to be as slow as a lot of things are out of the box. It might not be too bad. So that's kind of it. So there's this function, VM value, which actually I moved to the VM. VM value to static value. And it says VM values contain a lot of pointers to the VM stack and heap, which is currently just the host heap. We need to convert these into constants so that we can embed them in a binary, for example, LVM. This function does that by recursively loading all the values out of the VM value. Obviously, not all types are supported. For complex types, like a big slice of structs, I think we may just have to use some. Actually, this isn't true. Like, this is working. If you're nesting structs and enums and buffers, you're good to go. If you put something in there like a tree that has a raw pointer, you're SOL. But next up is to support references by simply loading the thing. So, we could get there, and that's representable in LLVM-IR. For every reference, you simply make a global, and that gives you static memory space to point to that thing, and then you put the pointer to that thing in the other constant value. So it does work. It is possible, and that's how buffers are working anyway. So let's run it. We have this. Maybe I can make a terminal here, right? So actually, let me try my new mode. So we can do. So I'll start off just by type checking this file, because what's fun about that is we'll see how much code actually executes, even though all we're doing is type checking. So we printed true equals false, which happens. We print goodbye world yet? Oh. We do see print output coming from the static code. And we have we print goodbye world at runtime. So let me remove my static crash, even though I wanted to get that message working. I can actually keep this in by saying test compile a static crash, which actually gives me a sum with the error message that the compiler spits out. So this actually gives me an option of string where the string inside is static execution exited with code 111. But we can actually see that up here. See, test compile, that crashing is sum, which means that's a compile error. And here we are, that all ran. I did say to do buffer of buffers. I'm scared to do that during recording, but maybe I'll try. This test is yeah, it's testing this bidirectional conversion because we have in buffer here. This runs the VM, and then to buffer, and then we have to take that buffer and reify it into static world. But then here in static code later, we're referring to int buffer, so we have to take that static buffer, which is like a Rust thing in the type checker, and turn it back into a runtime buffer, which means allocating space for each element somewhere in the VM. I do it in what VM calls static space, and for each item actually putting it there and then making a struct and then doing that. So that all of that code runs just when we say int buffer here. And then list wrap buffer is just a K1 function that expects a buffer, makes a growable list from it, and then we have a pointer to that struct, which is what L is, right? And we can push, we can call any code we want as if this is just a value because it is just a value. Let's take a look at static value to VM value for buffer. Right, so we're down here, and then we have our basic types, and right, buffer. Sorry, I was looking for it under struct because it's a special struct in everywhere else, but here it's a first class thing. It can't just be a struct because where would we put the vec? So we clone the ecovec that contains the elements. That's nothing. We want to get the layout of the elements. So how many bytes and what's the alignment, right, of each element of this buffer. And then we grab some memory on our static stack, and we push layout on init of of the element type. Which will only give us space for one element. So this may this may be really broken. For each element, we convert it to a VM value, and we offset our memory with it. We store it with the layout. We store it there. Then we make a buffer, which is just saying a little struct with the length and the data. The way I do this is I actually have Rust types that using reprc map exactly to the K1 types. So this is K1's buffer. So I can just make one and then like mem copy it. Using this push T, this will push any Rust type, which originally I was using to like push a U32 or an F32, but I can use it to push any Rust type because we'll simply compute the layout of that Rust type and then push it onto our stack. But yeah, I feel like if anyone then tried to use the static stack for something else, you'd be screwed because this is only allocating enough space for one element. which may be okay because it's only, I mean, it's not okay, but it may be currently fine because the only time we do this is this thing has its own VM. But if I tried to do this twice, let's see if I try to use buffer twice. Well, I just say amp buffer. That will load it, actually, if we don't do any optimizations. And then maybe that'll be enough to make it crash and burn, actually. Nope. One thing I want is some sort of static breakpoint, right? Where then the VM just pauses, and then I can look at the stack, which I do have helpers to dump the stack and inspect. Basically, wrote a debugger, really lightweight debugger, which is super fun. Where it would each expression, it would just wait for a read line from standard in and then keep going. So it's pressing enter to run each line or each expression. But this yeah, I don't know. We need it's like I want to call repeated. I haven't done this yet with my layout type, because I need to make sure it's aligned. Repeated, right? Because I can actually just log this, right? I'll just say pushing bytes for. Let's do it here. Bytes for buffer, layout dot. I just want to see it printing that it's definitely the wrong allocation. Should probably add a test, that fails, but it might be kind of difficult. So a layout is just a size of lines. So repeated, and there's Rust functions in std alloc layout. Let's look at what. Array. Layout describing the record TN TU size. So we're exactly array here. Classic. Unchecked mul. Just checked we want to overflow. U size when we multiply. Right, because their layout checks alignment, so. So I call mine array then? Well, let's just go back to the core. All we're really doing is multiplying n by element size. Sorry, element size being our size, yeah. I like naming it that. We're gonna go stride though. Element size padded. So this is just including end padding versus not, and I don't consider the size to include end padding. If you want that, then you have to use the stride. I'm gonna say let array size. Maybe we'll call it array. Cool. Come on, Copilot. Oh, it's sleeping today. Oh, and then we do everything in bits because we're dumb. So, because LLVM likes bits, and it uses bits in some places, and so I was tricked. But everything, especially in the VM, like when we're actually running this stuff, everything needs to be in bytes. So I have a big fat to do to convert my layout type to bytes. But, you know, we've got these helpers, and dividing by the constant 8 is not slow, even though, like, division is slow. Dividing by power of 2 constant is it's not the same thing. Let's just make sure we're bits. Still the same. Array. Array me. Array me. You get to name things what you want when you're having fun in your own code base. Okay. Let's go back to using just our old one. Pushing 8 bytes for buffer. And for buffer, let's ask our friendly module to static value to string me. Static value. ID? Yeah? No. No! I only have one that takes an ID. And this function, it doesn't take an ID. Christ. Whoops. You love when you press Shift Enter in Vim. Okay. See, even this one. I mean, I get why. I also don't know why you don't take the ID, because I have to call get. So I used to type gr for go to references, and then NeoVim updated and decided no. Now you have to type grr, and every time I go to references now, I just think George R. R. Martin. So let's George R. R. Martin, how many times this is called. So here we have to call get, so this site would be improved, this site would be improved. This is the definition. Why is that in references, by the way? Why is it in the middle of references? This site would be improved, this site would be improved, and this site would be improved. Well, the eyes definitely have it then. And then we just say values get and EAID. Is that good enough? No, because it's not part of the action. Fine. Your brain just doesn't work when you're recording yourself programming. This is a law of the universe. No, don't get it. Do that. Okay. We go back to buffer. Static value to buffer. Okay. I run you? What? There's a fly on my... Got it. Who? Oh, I messed up one of these. Come on. Come on. That one's okay. Mother... Pushing 8 bytes for a buffer of 5 I words. Each of those is 8 bytes. So this is definitely bogus. And let's switch to using our thingy. I'm pushing 8 bytes. Well, maybe we should log what we're actually using. That's why I didn't want to log it here. Hey, 40 bytes. 8 times 5. And let's use a type now that would actually have stride padding. Or I could just unit test the layout array thing. Do I have layout test? It's pretty bare bones, but this is not hard stuff. It should probably be better. Array. Me. So if we have empty and we array me 10 times, 01, maybe like this, and then I can say it's still 0 and the alignment should still be 8 and the stride is still 0, and then we'll do L2, which should be layout from oh. Ah. Wait, oh right, I use size up to a line, which is actually, I think, correct. So for this one, I don't have to do that. I just have to make one. So if the how do I make express a type here that has end padding? The size is 32 and the align 8? No. So it needs to be a type such that size is not a multiple of a line, right? Size is not a multiple of a line. So if we could be aligned to 32, if size is 32, it needs to be not a multiple of a line. Let me do it from Rust type because that's something I know. Rust type. Padded, and padded struct. So we'll start with what, 932, and then an I8, and then you can't just start. So the size, I mean the Rust size here is going to be 8, and the align is 4. But the actual size in my thing would be 5, because I do pad, but I don't do end padding. So the size is 5, not a multiple of a line. So right, so it would be layout size. It's 5. So 40. The align is 32. Rami 10. Well, I don't think I test stride anywhere, do I? Yeah. Let's leave this off. This will be L2. Size. Well, look, I'm not going to do that because it's a constant. But we will assert that its stride is 64. You got to go all the way up to the next one. Next multiple of 32. 40, next multiple of 32. Dun da da. And then what we'll do is we'll say L2.array 10 times. And what that should be is 640, right? You need 64 bits for each one. You got an array of 10. Align bits is still going to be 32, actually. And the stride of this thing is the... Yeah, if you're going to stack them on each other, that's going to be 640. That's divisible by 32, yeah. So that's going to be 640. Is this even right? I think this is right. Let's ask an LLM, and then let's also run it. Cargo test, layout test. We passed. Well, that's good. Does it pass with 641? What's wrong with you? No, fails. Great. I'm satisfied. I wrote a test. What a serendipitous little demo we had, right? I didn't even get to do what I was going to do today. So here's what's really fun. This is fine to manually construct things, but it's like, okay, how much of the language actually works when executed by the VM? Well, I have this test suite for the language, and I just call into all these other modules that test certain features, and I try to organize things like from low to high, so that if things break, it's more obvious to know, and we have building blocks, and we at least know this is working if something else is breaking. But I took all the lows and I put them in a function, and then now we run this at runtime. We also run low at compile time, and we just see where it breaks. So let me leave this out, and we'll run suite 1, our actual test suite program, and passes. It prints out a ton of stuff because the tests kind of like to print stuff sometimes, and I don't know what those colons are for. I don't think those are me, but then there's even like memory stuff going on, and pass. Does it work at compile time? And we actually get quite far, and we're panicking in the VM. So as you can see, VM execute expression call blah blah blah. It has a pretty deep stack. We're not going to talk about that. Not yet implemented function reference, and we get this really nice printout of where we were. So this is coming from inside the VM, and then we have this is actually coming from inside the VM as well. Function pointer K1 line 7. On this line, we try to turn we take the name of a function and get a reference to it, and that's function reference, and then we want it as a pointer, and we want to compare that to another pointer. And I thought this was a really interesting one to try to do in the VM. If we go to function reference, because what this code is trying to do is take a static function and say, give me a pointer to it. Why is that a problem? Well, that function doesn't exist in this runtime, right? In our VM runtime. These functions are just like some Rust data structures, right? There's no native function to have a pointer to. So at first I thought, I just can't support this, because any code that then tries to dispatch on that pointer, it would need to work, right? But it's not going to be a pointer to a function. So what do I do? Well, then I realized we control every time someone does try to dispatch on a function pointer, we get to execute that code. So we get access to that pointer. So what we could do is when you say, hey, give me this function as a reference, which is just a typed pointer. So we could actually stuff the function ID into that pointer. So we could actually just give you the function ID and say, here's a pointer. Now you can't do pointer arithmetic on it, which you can't do with function pointers anyway, right? To say, give me the function, 32 bytes after this function, because it's not going to be a memory address, and you can't dereference it, but you can't do that anyway with function pointers. So I think it's actually going to work, and I think you're going to be able to call these things and pass these pointers around. The K1 code will think it's a pointer, and then the VM will get it and interpret it as our typed module's function ID. So if we go with this functions, I'd say pub functions, not typed ability. So here is our whole program, our typed, database, essentially, in-memory database. And we have a pool of function ID to typed function, and this is the thing we need to call. And this function ID is just a non-zero U32. So I was thinking, I have 64 bits, so I'll pack in the function, I'll put the function ID in, and then I'll set the rest of the bits to like A's, so that like ASCII, maybe just Fs or the ASCII code for A, but then I would only have 4 A's, something like that, just so we can see it. I thought that would be fun, and then that's what I thought I would try to do for function reference. So, well, this is fun enough. Try and build this guy. So this function reference expr has a function ID and a type. That's great. So I have the function ID immediately. I'm actually just going to directly unpack this guy, and it's private, but there's a helper, not .0, but .to as I declare this with my macro because I have so many of them. I think I want get. We'll just go with as u32. Can it be a const one? What is this? Oh my gosh. One-shotted macro stuff because it didn't actually have it. You need to have any macro stuff in it. So the value I need to produce here is a reference. The type ID is the funref dot function reference type, and the pointer is robots in disguise function ID u32 function ID as putter. We'll go as usize Can I just go straight? We'll see. And then that's a value. And then this just produces an OK of a VM result that's a value with this value. And now reference to pointer doesn't have to worry about it because it's the same data, it's the same value. And we'll get back our same. We'll just do it as our u32. We'll print something. Println. I'm stuffing function ID into a reference value. Teehee. Okay. And then when we try to dispatch on that, I just hope we just get it to do. Might get more to dos. So we're failing in. Oh my goodness! I mean, of course that was never really gonna fail. And then we get expected enum on enum variant, which happens way more often than it should be happening. This is on building them, VM1631. Yeah, okay. So I'm calling building them from only one place. I'm only pushing them. Called from two places. The first is for static, and the second is running an enum constructor. Okay. This is actually what I was running into before, when I was running some different code before I got the function reference failure. K1 has enums, and the variants are their own types. They're first class types. And they function as subtypes of the enum, but I didn't really understand how to do subtyping correctly. And so I've done a mix of just allowing them where I expect an enum, and then also sometimes casting them. So we have values where their type says I'm the enum, but they're actually the enum variant, like by construction. And then the VM is choking on those because we're saying, hey, push an enum, and like here's its type ID, right? And then it goes here, and it's like, okay, I'm gonna push this enum, so let me figure out some things about it and let me look it up. And I expect to be an enum, and it's like, no, it's actually an enum variant, which is totally resolvable. I just need to I think I want to actually just insert some casts. So instead of the type checker just saying, oh yeah, a variant counts as an enum, that's fine, I want to actually, in those places, insert a cast from the enum to from the variant to its enum, if that's the type that's actually, that it says on the label, if that makes sense. This doesn't really matter because these types are the same layout, so they're interchangeable at runtime. So in the LLVM backend, it doesn't care, it works fine, but in the VM, where we depend more on this type data, I guess, it's ended up being an issue. Well, thanks for watching this this devlog. Sorry we didn't make much progress, but I think it's kind of a cool intro to the VM. Let me just walk through everything that did pass. So we got to oh, we're down here in enum construction, I think, or we were doing function pointers. So let me just come in here. So we'll do arith. So this is, my very most simplest, but this all ran. Bool test, char test, a little bit of string building here with append char, ability self call. This can all run at compile time. Whoa, I skipped a lot. I don't know what's wrong with me. Assign. So assignments and pointers, references to locals and things. Structs with pointers in them, and pointers with structs in them, and pointers to enums with data in them, and optional struct with a optional pointer to a struct with an int in it, right? All that kind of stuff, and it all passed. It all worked, and if I said assert false here, it fails. I promise. So ability 01. Let's get into bits test. This works, which is actually quite a lot more code to do in Rust by hand with all our int types than it is. This one's supposed to fail type checking, and it does. Control flow. So a little bit of FL stuff. My match test isn't running yet, but I know matches work pretty well. Did we get to while test? Maybe we didn't. Anyway, and that in addition to, of course, the static run. Some neat stuff in the built-ins too. So how am I doing this with, like, if you call crash, we can actually just check this, no SCD. We can actually do different things if this is static. So a lot of the core library code is going to be able to dispatch on whether or not the execution is static, which I think is really powerful. We don't have to build all that into the compiler. At runtime, this branch won't exist because this will be a constant false, and LVM will always remove it. It can't be compile time evaluated if, because when we compile this, we see that static is false, and we remove the static branch, and then the static code goes to run, and it just sees the live branch, right? So that's kind of funny. We would need some don't eliminate, or some first class thing for checking static, but leaving it as a runtime if that just points to an actual constant that's always going to be runtime known is actually working fine. So if it's static, then we're going to emit compiler message and then exit. Whereas, for our normal one, we do this backtrace stuff, which depends on libunwind, and we build a string, and we println, we sysexit. So, and this is an intrinsic. We would see it here with like error level when we emit message. And for memory stuff, these 4 functions are provided by the compiler. So for static execution, these point to my allocators, Rust's allocators, whatever we want to use. And then at runtime, of course, we're just going to use what the system provides, the libc calls. Same thing for memcopy, memset, and memcompare or equals. So yeah, it's starting to come together. The plan with all this static stuff is metaprogramming, like I said, to be able to just like run any code and then also have that code spit out code. A lot like what Jonathan Blow is doing in Jai, basically. I really think it's the way. Anyway, and I also think just like string manipulation, syntactic manipulation of the tree is really, really powerful. I think we see that by how good C macros are, how useful they are, not how good. And so providing the ability to do that, I think, is really important. Anyway, till next time.